Shear flow is a phenomenon that is the cause of a lot of headaches in the production cycle, including material degradation, molded-in residual stresses, service defects, shear imbalance, and many others. So what is shear? How does the flow of plastic create shear? Where is shear the most likely to cause issues? We're going to break all that down in today's advanced molding simulation topic for understanding shear stress and shear rate as a simulation output. During the injection molding cycle, plastic is subjected to large amount of shear forces as the cavity begins to fill. You can think of shear kind of like a deck of cards that you're pushing from the top. You'll note that the cards kind of at the bottom, closer to the table, have a friction with the table that prevents them from moving. However, the cards towards the top will actually begin to move if you push them forward. This is how shear is developed, and the friction that's created from the moving cards, in this case, versus the stationary cards is where shear is developed. All right, so understanding shear stress. So shear stress is a measurement of the tension created between the molecules created by shear flow. Note that this is a proportional equation where the shear stress is equal to the viscosity times the shear rate. So the higher viscosity you have, the more shear stress you can develop. Same thing with shear rate, which is more or less a gradient of the velocity of the flow. So the higher velocity, the higher the shear stress as well. That's why when you mold a little bit faster, you end up with a higher likelihood of shear stress to occur. In Moldex 3D, shear stress predictions are shown in a few different types of plots, but the most common of which is the shear stress plot. The shear stress plot shows us how much stress is in a particular region of the part geometry, but one of the most important things to note is that usually higher than 97% of the material is not necessarily at the maximum value that you see. So in this case, we have a maximum value of 0.391, so you might think that, okay, this region of the part is undergoing about 0.4 of an MPa of stress. However, that's not really the case because a majority of the part is actually kind of at the bottom of this histogram, indicating that a majority of the material is actually undergoing less than 0.2 MPa of stress, which is about half of the maximum in this case. Another important designation to make between the outputs of shear stress are shear stress versus maximum shear stress. Shear stress gives the value at the current time instant. So in this case, at 0.308 seconds, or the end of fill, this is the shear distribution. However, unfortunately, as the material begins to slow down, remember the shear stress is derived from the velocity of the flow. So as the material begins to slow down towards the end of fill, that shear stress is actually going to start to diminish. All right, so as such, we actually created this max shear stress result. This result shows the highest amount of shear stress experienced by each individual element throughout the molding process. So rather than just giving the shear stress at the current time instant, this maximum shear stress tells us the maximum amount of stress each element has experienced over the filling cycle in this case. All right, moving on to shear rate. Shear rate is the change in velocity as we saw back in the shear stress equation. So in regions of high velocity change, that's typically where you're going to get the highest amount of shear rate. So for example, when we're moving through the gate, we are decreasing our cross-sectional area typically when we're going through a gate, which means that there's going to be a high amount of shear rate where the velocity gradient is quite high, right at the corners of the gate typically. High injection speeds through thin walls and gates will often increase the shear rates, and in some extreme situations that can actually break molecular chains, which is more commonly referred to as material degradation. In Moldex 3D, the maximum shear rate result will show the recorded peak value at each element, very similar to what we saw in the shear stress earlier. Note that the maximum shear rate values are not tied to the current time instant. So when we look at a shear rate versus maximum shear rate result, even though both of these are at the 0.308 time instant, this shear rate is at the current end of fill time instant, whereas the maximum shear rate over here is actually the peak recorded value for each element, exactly the same as what we saw in the maximum shear stress. Because we're dealing with a non-Newtonian fluid, shear flow will actually change the viscosity of the melt. As the shear rate increases, the viscosity decreases. If we think of something like water, which is a Newtonian fluid, if you increase the velocity, its viscosity does not change. However, for plastic, because it's a non-Newtonian fluid, as you increase the velocity, remember shear rate is a gradient of velocity, the viscosity actually decreases. Because viscosity is the resistance to flow, a higher viscosity means that it's thicker. The lower viscosity means that it is, thinner, ultimately. So it flows much easier when we inject at higher velocities, which is why the injection molding process is typically a high velocity process. That's actually why we use polymers for injection molding, because of this shear thinning phenomenon. However, unfortunately, as we increase the velocity more and more, that doesn't just always lead to a decrease in viscosity. Ultimately, there's going to be some point where the force exerted onto the melt is high enough to actually break the carbon-carbon bonds in the molecular chains. Now, carbon-carbon bonds are typically quite strong. It's very difficult to break them, which is why plastic is quite flexible in the molding process. However, there is a point where you actually end up breaking these molecular chains. Now, the maximum allowable shear rate is a term that gets thrown around quite often, and most of the times you'll see a table such as this one, where every material has a maximum shear stress, a maximum shear rate, and you can find this from our website and a bunch of other sources as well. This is a pretty common rule of thumb table. But the thing to keep in mind is this is more of a guide. You'll note that these maximum shear rate values are rounded to the nearest 10,000. This is quite a difference between 30,000 and 40,000. There is a big gap between those two. And the reason why these are so generic is because there's no way to physically measure shear rates or shear stress. You can't take a probe and put it into your melt and say, okay, yeah, this is at 40,000 inverse seconds of shear rate. There's no way to physically measure shear rate or shear stress. Therefore, all of these recommendations are based on simulation correlation. The developers of such a table like this have taken a simulation with the same conditions as a real molding process, and if we experience a shear degradation, that's what's recorded as the maximum shear rate or maximum shear stress. And these usually have a bit of a safety factor put on top of them just to cover any sort of leniency in the molding process. Most of the time, you'll find that these values are difficult to hit for most materials, unless you have a very extreme process going on. So just note that this table, or a table similar to this, would be just a guide, and there is no physical correlation between shear stress or shear rate and any sort of measurement device. Alright, so moving on with material degradations, the key thing to mention here is that simulation is able to capture the shear rate and shear stress accurately. From a numerical standpoint, it's actually quite easy to calculate the shear rate. There's just not really a good way to measure it. And the reason that we're able to do so, especially in Moldex 3D, is that we use a three-dimensional mesh. This 3D mesh is very good at capturing the gradients of results in the injection molding process. And like we mentioned earlier, shear rate is really just the gradient of velocity, or the change in velocity across the thickness. Just to look at the boundary layer meshing technology that Moldex 3D uses, we do have a video up on the YouTube channel for this topic specifically. But we can see here that we have a 5 layers BLM in the runner. We've used a 3.0 offset ratio for the runner in this case. We did go a little bit light on the part, but we actually see that there's a part insert here in green, and that is using a pure tetra type mesh. So a prism, or this boundary layer meshing, uses a prism or a hexa element in this kind of rectangular region. As you see, these are what we call second order elements. They're very organized, as you can see, in contrast with the tetrahedral elements up here. The prism and hexa elements are very good quality elements. They're able to capture the information in high precision, whereas the tetrahedral elements are less organized, but they are still actually quite good at capturing things like temperature and velocity. The most important thing is to be able to capture the velocity gradient right at the frozen layer, which is usually just inside the surface. So that's why we want these boundary layers to really consist of a majority of the thickness of the part, or as much of the thickness of the runner in this case, because we want to be able to capture that using these higher quality elements. And even for a more complex geometry such as this one, we're still able to create a very, very high quality mesh, which gives us the ability to study things like shear rates, fiber orientation, and many other things. With the current technology of 3D simulation and material characterization, shear flow is actually able to be captured pretty well. As we can see here in the flow through the gate, we actually have a pretty high velocity through the middle. That's usually where the velocity is the highest. But you'll see actually that that's not where the shear rate, which is what we're looking at here, that's not really where the shear rate is the highest. The shear rate is actually the highest over in here where the velocity change is the highest. Remember, the shear rate is not the velocity, it's the change in velocity. All right, so as we get over towards the edges where the material is maybe not moving as much over here, we do get a higher shear rate because of the compression of the melt through this lower cross-sectional area region. One other thing to note about the shear rate tables is that they are actually based on a 2.5D meshing technology. And that's usually why those values have such a high safety factor placed on them, is because they know that there were inaccuracies back when the technology wasn't as high as it is right now. So it's always recommended to use caution when utilizing those tables. Right, the interpretation of shear rate results is extremely important. We're always going to get a high shear rate value towards the sides of the gate, or towards the mold surface, if you will. But what we need to keep in mind is that a majority of the melt is going to be experiencing this shear rate through the middle of the gate, not necessarily what's at the sides of the gate. So as such, we always recommend you to not necessarily take this maximum value. In this case, it's about 400,000, which, if you remember from the table, most materials are below 100,000 as far as the maximum value is concerned. So you would see this value and you would say, okay, well, my process is not very sufficient. But really, what ends up happening is, in most situations, the highest shear rate is actually just towards the sides of the gate, which only a small percentage of the material actually experiences across the thickness of the gate. So really, in this region here, we have about 1,000 inverse seconds. This is a different case than the previous one, just to make everybody aware. This is about 1,000 inverse seconds in the middle versus about 4,000 inverse seconds out towards the side. So just in this gradient alone, we have about 3,000 inverse seconds of a difference, which the magnitude of shear rate might be difficult to conceptualize, but just know that the majority of the melt is actually going through maybe like the 80%, the inner 80% of the gate. So if I were to take the average of this plot, we would see that the average is more around 390 instead of the maximum, which is about 4,200. Okay, so this is all to say, just don't just take the maximum value of shear rate. You always want to be looking at the histogram plot, which allows you to really see where the majority of the melt is actually experiencing. This same phenomenon can actually be said for shear stress as well. Usually the highest value of shear stress will not necessarily indicate the true value. Most of the time, the maximum value for shear stress and shear rate, for that matter, are usually just one or two elements that have experienced a local maximum. So really what we want to do is we want to break this result down and see what the actual value is of shear stress in a particular region. We do that through what we call the isosurface tool. The isosurface tool just allows us to kind of see these the regions of high stress, not necessarily just the values of high stress. Okay, so now that we understand shear flow from a fundamental standpoint, now we need to look at how that shear flow actually impacts the molecular orientation. Thermoplastics are typically just long carbon chains. These carbon chains are typically tangled up with one another. They don't really like to be straightened out because that would induce a stress on the molecular chain. The stress-free state is typically coiled something like this. When you pull these molecules, you actually can straighten them out, but that actually is not the relaxed position for those molecules. The relaxed position is actually something more like this. So when you pull these molecules and force them to be a little bit straighter, this is an induced residual stress. This pulling of the molecular chains is very synonymous with what happens in the filling process for injection molding. Depending on the part's wall thickness, the molecular chains may not have time to recoil before they're frozen, and therefore for thin wall parts, most of these chains are going to have some sort of induced stress as they begin to freeze. They're not able to go back to their relaxed state like this one over here. If the cooling is not uniform throughout the wall thickness of the part, then you actually get another induced stress on top of this flow-based stress, which is called thermally induced residual stress. And both of these effects will compound with one another, impacting the warpage, the mechanical properties, and in some cases even the surface quality. Looking through the thickness of the part, we get a high molecular orientation out in the frozen layer. Right inside of that, we actually get a pretty high molecular orientation where the material is undergoing a large shear effect. And then in the middle, there's not really that much shear rate because the velocity gradient is not that high, so the orientation is not very high. Looking at a couple of common surface defects, first of all, we get what's called a stress mark. Stress marks typically caused by either a high amount of shear stress in a particular region or, more importantly, a gradient of shear stress, which can actually be even more dangerous for certain materials. This is what we call tiger striping, where you get a kind of a recurring stalling out of the melt front. So the melt front will go, stop, it'll go, stop, go, stop. And because the shear rate is a gradient of the velocity, as the velocity changes, we get actually a high amount of shear rate in the part at different stages. And that's kind of what we're seeing here. There's actually a bunch of kind of stripes that occur throughout the part as the melt front kind of stalls out and begins flowing again. This over here is another shear-related defect on the part right at the gate, and we actually see that right after the material gets through the gate, we actually have a pretty high velocity gradient right at the surface of the part, and that actually caused a small amount of cracking. And then over here we get an optical stress plot. This is what we call a fringed pattern. And wherever you go from a yellow color to a black color, or orange and black over here, that's where there's a gradient of stress. Gradient of stress, as far as optics are concerned, actually impacts the visual quality of something like a lens. If you were to look through a lens, you'll actually sometimes see these visual defects. So you can see that right at the gate, which is at the bottom here, that's where you're getting a high amount of stress gradient. All right, and then finally, burning due to shear heating. Whenever the material is moving through the runners, we actually get a shear heating phenomenon, and that can cause burning if the stress induced by that shear heating is too high. So we're going to look at shear heating in a little bit higher detail, and the thing you need to know is that the highest amount of velocity gradient is going to be just inside of this frozen layer. This velocity gradient again causes a high amount of shear rate, and that's really where you're going to get a shear zone, as we call it. So the shear zone is out in the red regions here, and then in the middle of the melt there's not that much shear because the velocity gradient is pretty much zero. Alright, so shear induced imbalance as a concept can be shown through this very simple 4-cavity mold. We have a perfectly geometrically balanced runner layout where the flow length to each of these cavities is exactly the same. However, we actually get a pretty obvious difference in the flow through this runner. As the moving material in the runner rubs up against the frozen layer in the runner, that is actually going to cause a high gradient of velocity, which will cause friction. That friction will actually heat the melt, or thin the melt, as you can think of it, causing a lower viscosity out towards this side here, and this side down here. When we make this turn, when we make this 90-degree junction, the cold material traveling through the middle actually goes towards the outside, where the sheared material actually comes through the inside. This creates a left to right imbalance. The material on the right side is at a lower viscosity because it is hotter, because the shear rate is higher. And that actually ends up carrying through the next 90-degree junction, where the hotter material actually just continues over here, colder material continues over here, and we get a flow plot that looks something like this, where the material flows into these two cavities much easier than these two cavities. But even within one single cavity by itself, this side actually fills at a higher temperature, which will actually impact the shrinkage of the part. So even isolating the other 3 cavities, this cavity will actually undergo warpage because this side is going to shrink at a higher rate than this side due to the temperature imbalance. Another way that you can look at shear rate through the runner is by using a slicing view. And we can very obviously see, if we were to take a slice through our runner, we actually get a pretty cool view of the shear rate. You get a shear ring right in the middle here for a cold runner. Note that this is for a cold runner. We'll look at a hot runner in just a moment. But for a cold runner, you actually get the shear ring. You're not going to get a whole lot of shear in the frozen material, but the material just inside of that is going to experience a high amount of shear rate because of the velocity gradient. And in the middle, obviously, we don't have much of a velocity gradient, therefore the shear rate is quite low. All right, looking at a cold runner versus a hot runner, they actually, the plots themselves look a little bit different, but both plots actually show the exact same phenomenon. So again, these are both shear rate. Left side is a cold runner, right side is a hot runner. In a cold runner, you see that shear ring through the middle. However, in a hot runner, there is no frozen layer, so the velocity gradient is actually starting directly from the mold steel. So both of these types of runners, although they're slightly different because there's no frozen layer in the hot runner, they actually do undergo the exact same phenomenon, and you'll actually see that the shear-induced imbalance through a hot runner system is actually going to follow the same trend as a cold runner. And here's just a little bit better of a view, the slice through a hot runner for shear rate. In cold runners, you get the shear ring kind of closer to the middle inside of that frozen layer, whereas on the hot runner, you get it right on the outside. All right, wrapping things up, plastic material is subject to large amount of shear forces during the filling stage of the molding cycle. shear thinning and heating have a big influence on the injection molding process, not necessarily only from a surface defect point of view, but also from a progression point of view. We saw a shear-induced imbalance. We also saw shear marks. We saw a bunch of different effects that are all caused by the shear forces experienced by the plastic during the filling process. Higher shear rates can actually deform or break molecular chains, which is where shear degradation is derived from. Maximum shear rate tables were developed decades ago based on a little bit of an older meshing technology, so you should always be careful when using those shear values for your simulation. They can be used as a general rule of thumb, but I would never use them to constrain my molding process. Using the more modern 3D technology, looking at the shear rate across the thickness is really the better way to be visualizing these results rather than just comparing the maximum values to a table that was developed a really long time ago. Surface defects can be caused by molded in stresses, things like flow lines, burn marks, tiger striping, warping, and many others. And then shear heating can be avoided using simulation early, but they can cause a lot of issues down the line if you don't anticipate them. Thank you for watching today's advanced molding simulation topic for understanding shear stress and shear rate as a simulation output. And we hope to see you at one of our live events soon. You can sign up for those on our website, moldex3d.com. And the live events include conferences with live presentations from users and Moldex 3D personnel, short webinars on topics like this one, and full demonstrations and trainings for the software. Go beyond simulation with Moldex 3D.